So welcome everybody to this second meeting of the SID seminar. And today it's my pleasure to have Orphée Collin talking about the random field Ising chain in the case of center disorder. Thank you.
Thank you. Thanks for the invitation, and glad to speak in front of you. So this is work I did during my thesis with Giambattista Giacomin, Raphaël Greenblatt, and Yun Hu. And my defense will be that next week. So the slides are still a bit sketchy, but it's going to be okay. So I'm going to talk about the Ising chain is a very simple model of a very simple case of the Ising model. So you can look at sites on a line graph, and so the pure case is going to be easy to consider, and we're going to add a random field, which may make things more interesting. But let me first start with the pure case. So there is the definition. We have some parameters. So first is n is a positive integer, which is the size of the system. So you have capital N sites from 1 to n. We're also going to have an interaction parameter gamma positive, and boundary conditions, which I showed here with the red disks. So full disks means +1, and empty disks means -1. So our configurations will be spin configurations, so collections of plus and minuses on these sites. Okay, I think okay, and we put a measure on this configuration space by considering the following Hamiltonian. We just count the number of spin changes in the configuration, and we penalize them by a factor gamma. So we penalize because we define the measure to be this Gibbs measure. So it's proportional to the exponential of the Hamiltonian. And of course, we have to normalize it by what is called the partition function, which is the sum of the numerators. Here you see that the boundary conditions intervene in the sum here. The case n equals 1 has the indicator that there is a spin change between 0 and 1, and the case n equals capital N plus 1 counts the presence of a wall between n and n plus 1. Okay. So I'm going to give a quick analysis of this model. In fact, okay, just some vocabulary which are already mentioned, perhaps. So the sites with consecutive sites with the same spins are called spin domains, and we consider that the spin domains are separated by spin walls, which I presented using dashed lines. So this is the structure of spin domains, spin walls. So to analyze the pure case, let me slightly change the boundary conditions. So I will use 3 boundary conditions on the right side first. This means I'm simply removing the n plus 1, the last term in the sum. So we just forget about the boundary condition on the right. It's free. We still have the boundary condition on the left. Why did I do this? It's because in this case, we can make the measure completely explicit. So the partition function is just this, because in fact, for each site, you can choose whether you change spin or not, and you have, and since there's no conditioning on the right side, you can have all possibilities. So the measure factorizes out in this way, and you can read on this formula that the variables here which indicate the presence of walls, are independent and distributed as Bernoulli variables with parameter exponential minus gamma divided by 1 plus exponential minus gamma. Okay, so spin walls appear independently with this probability. So the spin domains are i.i.d with lengths distributed as geometric variables with this parameter, and we understand the model very well. It's fairly easy. In particular, for very large systems, the density of walls converges towards this p gamma. Also, when we are far away from the left side, the left side, essentially the marginal distribution of sigma n is uniform over -1 plus 1. In fact, the convergence is exponential with rate p gamma. And also, if you consider two independent configurations under this measure, typically they're going to overlap with density one half. So I stated it in this way. So the fraction of sites, sorry, there should be an index n here. The fraction of sites where sigma 1 and sigma 2 differ converges to one half in distribution. You can have concentration inequalities here and there to quantify the convergences. This is fairly easy. And if now we come back to the case of a boundary condition on the right side, you're simply adding a mild conditioning, which is on the parity of the number of walls. But so they are not the lengths of the spin domains are not exactly i.i.d, but the conditioning is not is mild, and you recover all those results also. Okay. Let me show you some simulations. So here I used so the system is of size 100, gamma is equal to 3. And I used boundary conditions plus, which are not represented this time, but okay, there, yeah. So typically the length of the spin domain should be exponential 2 gamma plus 1, so exponential 6 plus 1, which is around, yeah, something between 10 and 100, I guess. So, okay, so this is very well understood and simple. But now the philosophy of disordered systems is to ask whether adding a bit of noise changes the behavior of the system. So in this context, adding a bit of noise will be adding an external field which acts on each of the sites. And actually this noise is going to be taken as the realization of an i.i.d sequence. So we consider an i.i.d sequence of centered random variables with a second moment. And we assume that the law is not degenerate. For example, you can consider the Gaussian law, and the variance will be denoted by theta squared. And then for every realization of this random walk, we're going of this sequence, we're going to consider a Gibbs measure, so which is going to be a random Gibbs measure, so defined in the same way as before, but we add this term to the Hamiltonian. So each spin interacts with the field at the site. You can imagine that there are arrows on each side, and the spins want to align with the local field. So if Hn is positive, sigma n is encouraged to be +1, and otherwise it's encouraged to be -1. And of course the strength of this behavior depends on the absolute value of Hn. So there are two antagonist behaviors in the system. each of the spin wants to align with the local field, but they also want to be aligned with their neighbors. So there is a trade-off we are going to analyze. Okay, is there any question at this point on the definitions? Okay.
Really, but does this model have a phase transition somehow?
We're going to see that there is what we call a pseudo phase transition as gamma goes to infinity. So we're going to see interesting stuff happen when gamma goes to infinity. So the aim is to study the relevance of disorder. So to see if adding this disorder sequence modifies the behavior of the system. And so we're going to work with a fixed intensity. So a fixed, essentially, so you can think of theta as the variance, the theta squared as being fixed. And we're going to take gamma, the intensity of the inner interactions, to go to infinity. And we're going to see that even if gamma goes to infinity, the field still plays a huge role. So here is a simulation. I took now a gamma equals to 5 and also boundary conditions plus. So this times the red is for plus and the blue is for minus. And above, you can see I represented the environment, so the sequence H, by in fact representing the random walk which is associated to H. And okay, here gamma is not very large because okay, it's difficult to simulate this model. Well, I did it quite naively using Glauber dynamics. I let the dynamic run for long enough. But okay, but this is exponential in gamma, so I could not have a very large gamma. Already for gamma equals 5, we can see that there is apparently some kind of region here where the spins want to be minus, except for sporadic spots where there are some plus regions. Also here, we see pluses, but with also sporadic minus regions.
I'm sorry.
Yeah.
Next question. What are the different lines? Do you suggest samples? Or?
Five different samples, yeah. Independent, yeah. And okay, so in the representation of S, I marked different positions here by vertical lines, which we're going to talk about later. But okay, as you can see, the red ones correspond to high values, and the blue one to low values of S. And it seems that the simulation, the samples are somehow in accordance with these points. So we're going to see that in more details with some theorems. But let us first talk about the free energy. So in the pure case, we had an explicit formula for the partition function when the condition on the right is free. But in fact, for all boundary conditions, we can show that 1/n logarithm of the partition function converges towards log of 1 plus exponential minus gamma. And in the disordered case, we can show that there is a limit, so there is a free energy, and it does not depend on sorry. So for almost every realization of the disordered sequence, we're going to have the convergence towards some quantity f gamma, which does not depend on the sequence. It depends only on the law of H, of course, and on gamma, but it does not depend on the boundary conditions. So this is fairly easy to establish using Kingman's additive algorithmic theorem. But we're going to investigate a bit more on f of gamma, and in particular, it's asymptotics as gamma goes to infinity. Okay, so here are two results. So The first one is for concerns the first order of gamma, but it has the less it has the weakest conditions with respect to the second one. So if you just admit that the disorder law is has some moment of order p slightly larger than 2.6, then the first order is just the variance of the disorder divided by gamma. And in the second theorem, we make more hypotheses, but we obtain a better development, more precise. So the first hypothesis is about some regularity of the distribution. So we don't assume that it's the distribution has a density, but iterating the convolution product, we get a density at some point. Also, we assume that mu is the law of the HNs. We assume that the law of H1 has a moment of order larger than 5, and then we get this development, expansion, and it's quite interesting because it's quite regular. Okay, this goes to order gamma minus xi minus 4, but in fact there are only two constants that appear there, so it's quite regular. All the terms are going to be expressed easily in terms of kappa 1 and kappa 2. Okay. In fact, if you have exponential moments, you are going to have all the polynomial terms of the expansion. So it's quite. We don't quite understand why it's so regular. Okay. Using the first theorem, we can of course show that kappa 1 is simply the variance of the disorder, which was also quite stunning because in this theorem, the value of kappa 1 is given in a very unexplicit way, and okay, this was proved. This was proved after, in order to show that kappa 1 is equal to the variance. In fact. Okay, so let me say a few words about the proofs. So, okay, let's start with the first one. As I wrote, you use a continuous model, which in fact arises as a weak disorder limit. Maybe I will talk about it later if I have some time. And for this continuous model, the free energy is exactly computable, and so we can and it has the order 1 over gamma, and so if we perform a coarse graining, we can compare the partition functions of the discrete model and the continuous model. The coarse graining is quite long. It's a full article, but that's the general idea. And for the second one, I'm going to give some more details, because it's quite interesting because it's related to random matrix products. So I'm going to show you the free energy is related to the Lyapunov exponent of a random matrix product. So let's recall the definition of the partition function. It's given here. And actually, I claim that it's interesting to look at this product of matrices. So you have matrices that with different type alternating. So there's this deterministic matrix which is repeated, and those matrices, those diagonal matrices which are random, they just depend on the HNs. And actually, can you guess what's the result of this product? For example, let's consider the coefficient 1, 1 of the matrix we should obtain. So this coefficient is the sum of all the possible paths you can take throughout these matrices. And you have to respect, of course, the rule of the matrix product. So, for example, you can start with coordinate 1 and then jump to stay in coordinates y for a while. Then here you can jump to coordinate 2. And in fact, you're going to see that you're summing over the all the spin configurations, and you're recovering exactly the exponential of the Hamiltonian. So in fact, you're going to get the different partition functions with different boundary conditions. So those partition functions can be compared. I mean, they're just of the same order. They can be compared with each other up to factor exponential 2 gamma. So they all have the same exponential growth rate, the free energy, which I mentioned earlier. But so it's also the Lyapunov exponent of this of a product of matrices. So let me just mention what is a Lyapunov exponent. If you have random matrices M1, M2, Mn, if you consider any matrix norm, then this converges towards the Lyapunov exponent associated to the law as well. Sorry. So the existence of this limit is also fairly easy to obtain using the Kingman's subadditive ergodic theorem. For example, you can, because it does not depend on the chosen norm due to equivalence of norms in finite dimension. So you can take a submultiplicative norm and easily show that this conversion occurs almost surely and in N1. Okay. But what's more interesting is that the theory developed by Furstenberg yields an explicit formula, not explicit, but yields a formula for the Lyapunov exponent. So just a small thing here. I want i.i.d matrices and these alternate types, so I need to group them somehow. What I did was to forget about this one, because it's not. Forgetting about this does not change the exponential growth rate of the coefficients. And then I grouped them 2 by 2. So I considered those matrices here. For convenience, you can decide to divide by exponential hn. So you get rather this matrix product with epsilon equals exponential minus gamma and zn equals exponential minus 2hn. Dividing by exponential hn does not change the exponential growth rate because hn is centered. So by the law of large number, 1 over n sum of hn goes to 0. So it's equivalent to consider the product of these matrices. And this was already tackled in a work by Derrida and Hilhorst. Okay, so this what's the formula given by the Furstenberg theory? Well, you have to consider the action of your random matrix on R2, and actually, what's really important is on the projective space. So how it acts on the quotient of the two coordinates. So that's why I took here the second coordinate is equal to 1. And I also chose the parameterization of exponential of x, which is for convenience. So the action of the matrix on this vector gives this vector. So in this parameterization, the action of the matrix is this recursion. And it's so I introduced the function b gamma, which is this one, and I'm going to plot it afterwards. So we have this recursion. Hn is random, so this is in fact this defines a Markov chain, and in fact the Furstenberg formula expresses the Lyapunov exponent. So in our case, free energy as an integral formula involving the invariant measure of this Markov chain. Okay, this is not very nice looking, but what you should just keep in mind is that we need to understand precisely the invariant measure, probability measure, sorry, next to gamma. So let me show you first what is b gamma. As you can see, so here for gamma equals 4, gamma equals 10. Okay, there are two asymptotes, so it converges in minus infinity to minus gamma and plus infinity to plus gamma. And in the bulk of the system, so not too close to the boundaries, to minus gamma and gamma, sorry, not too close to minus gamma and gamma, it's essentially the identity function. So your recursion is here is essentially your if you're between minus gamma and gamma and quite far away from them, you're behaving like a random walk. And if you get close, you have some force that puts you back in minus gamma gamma. So there are soft walls at minus gamma and gamma, and these are some simulations of the invariant measures for different disorder distributions. And so the first case is the nicest, which corresponds to the hypothesis of the theorem. So having a density, essentially. So in that case, things behave quite well. You can see that it's the invariant measure looks like the uniform measure minus gamma gamma with some differences on the boundary, but okay. Here we took a lattice distribution and things get more messy. That's why the theorem is not going to work with distributions which are not regular enough. Here also there is an atom under continuous spark, but already things are a bit ugly. Okay, so as I said, we need to understand precisely the invariant measure near gamma, so on the right side. And there was a heuristic given by Derrida and Hilhorst in a work in 1983, which we made rigorous, which is to consider that, okay, we have two walls at minus gamma and gamma, and we so in here we have two walls at minus gamma and gamma, and we can treat them as we can consider two semi-infinite systems. The system where there is only a wall at minus gamma, and the system where there is only a wall at gamma. This yields two invariant measures which are of course infinite, but if we patch them together at 0, this gives a good candidate for an invariant measure. And then you need to show, okay, so you need to control very well these two semi-infinite measures, and you need to okay, so we patch them together, and you need to have some contraction argument to show that this candidate is quite close to the true invariant measure. And then you have a very good description of what's going on next to gamma, and you can conclude the proof of the theorem by exploiting the Furstenberg formula. Okay, is there any question?
That in second theorems, when you have higher moments, then the rate of decay of the error is better. Can you explain about that?
So this fact, yeah, because you need to so if the measure is satisfies, if the disorder law satisfies the hypothesis, then you're going to get something which is quite flat here. But you need to see how flat, and so you need to understand in these two semi-infinite invariant measures what is the how quickly it's going to converge towards something that's flat. And to control this, we use it's quite long, but we use renewal theory, the renewal theory, fluctuating theory, the renewal theorem, and to use the renewal theorem, we need some moments. So the precision of how we control the flatness here then has an impact on the precision of our estimation here. So let's now look at consequences of these theorems. So of course, we have already seen that the behavior of the free energy is different between the pure case and the disordered case. It's not the same order as gamma goes to infinity. And in fact, we can already deduce some things. We can already deduce the mean density of walls in the large n limit, simply because of this observation, which is very classical for statistical physics. If you derive if you derive the log of the partition function with respect to parameter gamma, you're going to recover the expectation under the Gibbs measure of the term that appears in front, the term in the Hamilton in which the gamma appears in front of. Okay. And so if you take n to infinity, then and using some convexity, you obtain that the mean density of walls is given by the derivative of the free energy with respect to gamma. So in the pure case, we recover 1/1 plus exponential gamma. So the p gamma that we had in the analysis of the pure case. This is okay. And here we get the variance divided by gamma squared. So this suggests that the walls appear at a frequency. But this tells us that the walls appear at a much larger frequency in the disordered case than in the pure case, at least for gamma large. And now we're going to investigate how this goes at the level of trajectories. And there is a first simple heuristic argument by Imri and Ma, which goes back to the 80s, I think. So if you consider you start with, sorry.
We have a question from someone online, yeah. Maybe. I don't know if the question is.
I don't know.
Yeah, we can hear you.
Okay, good. I have a question about the Furstenberg formula. It's not the one that I'm normally familiar with. You derived it from something, or?
Yeah, well,
sorry, I may have not been paying attention and missed that, but yeah.
It's okay. I could derive it by hand. But I don't want to spend too much time on this. But actually, here with two by two matrices, you can really do it by hand and express you can express the partition function in this way. So the free energy, the Lyapunov exponent in this way. This is the so normally you have an expectation of the action of one matrix. How is it already? No. I don't. You take. I don't have it exactly in mind, so I'm not sure if it's like this, but you integrate under the invariant measure the expectation of the growth rate of applying one matrix. So here is the expectation on the law of M1. And here it yields this, I guess. But yeah. Maybe during the questions I can make the explicit computations. Okay, so let's consider this very simple heuristic argument. We start with a configuration with pluses everywhere, and we look at the sides from n+1 to n plus capital L for some n and some L. We wonder what happens if we switch the spins in this region from plus to minus. So this is going to modify the energy by okay, -2 gamma, because you have to pay for 2 additional walls, and also -2 times the sum of the HJs on this on this domain. -2 because you go from having plus to having minus, so there's a factor 2, and so this can be and if L is large, this sum is distributed essentially as a Gaussian with parameter theta squared times L, so it's of order theta times square root of L, and so if L is of order gamma squared divided by theta squared, it may be that this Gaussian variable is smaller than minus gamma, so the overall quantity is positive. So it may be that this stretch is more, this domain is more favorable for having minuses than for having pluses. Okay. Okay, so this argument suggests that the structure, the domain wall structure is at a scale gamma squared over theta squared. So this is coherent, consistent with what we got with the free energy. And also it suggests that the domain wall depends strongly on the disorder. It's the disorder sequence which decides which regions are more favorable for minus domains or plus domains. And we're going to refine this Imrima argument to get a precise description of the random domain wall structure. And this will okay. The work is based by considerations by in the physics literature by Fischer, Ledoussal, and Montus, and we're going to use a key ingredient, which is the notion of gamma extrema of the walk S. So let's first wonder what is the spin configuration which maximizes the Hamiltonian. So I sometimes say also energy instead of Hamiltonian. So if you start from one configuration, so let me represent the walk S associated to H. Let's say we start with a configuration like this one, and the boundary conditions are plus plus. Okay, so here you have a domain of plus, a domain of minus, and a domain of plus. You can try to increase the energy by, for example, moving a wall around. For example, you can move this wall from here to there, so like this. then you have, instead of having this energy difference, this energy difference negatively, you have it positively, so you gain some energy. Also, you might, want to introduce here. Here you see that there is a rise in the environment. You might want to introduce a domain of pluses here, and it's going to be, in fact, it's going to be to increase the energy if this height difference is larger than the parameter gamma. Okay, so there are these different ways of increasing the energy. Just moving a wall around, or introducing a spin domain, or removing a spin domain. And actually, if you do so, if you increase the energy as long as you can, then you're going to end up in a configuration which is with maximal energy. In general, there is no unique maximizer. However, if you assume that the disorder law has no atom, for example, then the maximizer is unique. We call it the Fisher configuration. So, because Fisher described it in his work, but he obtained it, Fisher and Corfus obtained it using renormalization group fixed points. So here is an illustration. I use a bilateral random walk for simplicity, so that there is no question of what happens at 0, but you can adapt the definition. So these are your maxima, minima, and they are defined here. So we say that a site N is a gamma maximum for S if you can exhibit. So for example, U2 is a gamma maximum if you can exhibit A and B such that S is maximal at U2 on the interval AB, and the height so Sn minus Sa and Sn minus Sb is larger than gamma, and so you can think it as in this picture, U2 is the what do you say, the pit. Comment dire un sommet? U2 is the peak of a mountain of height at least gamma, and U2 is the bottom of a valley of depth at least gamma. You can, okay, so this is the definition of a maximum, but you can define it for minimum likewise. And so you have alternating minima and maxima, and in fact, so the energy with maximal configuration is exactly the configuration with maximal energy is exactly the configuration which reflects these gamma maxima and minima. So it's equal to +1 on ascending stretches and to -1 on descending stretches. So it's an exercise to show that it has that it maximizes the Hamiltonian, and the claim by Fischer, Ludussan, and Mutus is that the typical configurations should be close to this configuration, which is okay. So close, we're going to have to say what close means, of course. But let me just give some information on the statistics of these gamma stretches. So first, these times are not stopping times. However, they define portions which are i.i.d. up to the sign, of course, and so they are renewal events, sorry. And if you look at the height and the length of a generic gamma ascending stretch, then you can express them using fluctuation theory, but it's not very explicit. However, you can characterize the limit as gamma goes to infinity. Indeed, you can use Donsko's theorem. So the random walk converges towards a Brownian motion, a centered Brownian motion, and for the Brownian motion, this process of gamma extrema has already been studied by Neuve and Pittman in '89, and they give an explicit the explicit distribution of the pair for the pair of the height and length of a generic stretch for the Brownian motion. So we can show this convergence. So we can understand fairly well these variables, and in particular, we get the Brownian scaling. So the length of order gamma squared, as you can expect. And in fact, the distribution of H is fairly simple. It's just 1 plus an exponential of parameter 1. So the height of a stretch is distributed as gamma plus gamma times an exponential. So the excess is also of order gamma.
What is 1 plus exponential of 1?
So if I denote by H gamma the height of so just the height from the bottom to the end of the stretch, this is distributed. So H gamma divided by gamma converges towards 1 plus an exponential of parameter 1.
Yeah, I don't understand. It's a constant. You say it's distributed as a.
No, sorry. I mean that this is a random variable. So H and L are two random variables.
Yeah.
The joint law is explicit, but I did not write it. I just wrote the first marginal. So the first marginal is 1 plus exponential 1.
An exponential random variable.
Yeah, sorry, I mean, yeah, so it's distributed as 1 plus plus E, where E is an exponential variable with parameter 1. Okay. So this is a convergence in distribution. Okay. So here are some simulations to illustrate this. Here I showed the S, the random walk associated to the disorder sequence, and I have plotted the maxima and minima. So the gamma minima are in blue, the gamma maxima are in red. Here gamma is equal to 20, and below I also plotted the probabilities of sigma j equals +1, and you can see that in the ascending stretches the probability is close to 1, and in the descending stretches it's close to 0. Essentially, there are some flows, of course, not exact. And I can now show you an example with gamma larger, gamma equals 100. And you see that it's even sharper. It's even more, even closer to the 1. Also with some flows remaining, but there are less of them. I'm going to explain in a moment how we can compute this probability. But first, let's give the theorem. So the theorem states what Fisher and collaborators have claimed, which is that the typical configurations under the Gibbs measures are close to this configuration sigma f, Fisher configuration, in the sense that the fraction of sites where the sigma disagrees with sigma f converges towards some quantity d gamma. And this quantity is small, and it goes to 0 as gamma goes to infinity. And we have a control which is log gamma over gamma. Okay, so this means that essentially up to first order, the trajectories, so the configurations of this model are really close to this Fisher configuration, which is random, but it depends on H as the measure, the Gibbs measure itself. In fact, this control is quite sharp because we have arguments to show that d gamma is at least of order 1 over gamma in the Gaussian case. In the Gaussian case only because we use overlap arguments which are usual in replica computation. So is the question on the theorem? Okay, so I'm just going to sketch the proof. So if you, so we're mainly interested on this probability and showing, as the simulations suggest, that this probability is either close to 0 and to 1, and with corresponding to whether you're in an ascending or descending stretch. So let's first try to express this. So to express this this probability, we consider the event that sigma n is equal to +1. So if you assume here that you have so you need to compute to consider the contribution of all the configurations that have sigma n equals +1, and in fact you can see that this is equal to what I wrote here in the numerator, because if you fix what's going on here, then you have okay, the exponential of hn, because you gain hn, but then you have two independent systems. You can divide into two systems. The system between 1 and n-1 with boundary conditions, your initial boundary condition at 0 and the condition plus at n, and the system on n+1 n with your initial boundary condition here and with the boundary condition plus here. So this is what I wrote in the numerator, and in the denominator you have the full partition function, which is you can divide into the contributions given by those configurations which have sigma n equals +1, so the same as the numerator, and the configurations with sigma n equals -1, and this is what you get, which essentially you change plus into minus. Now if I divide everything by the numerator, I get those 1/1 plus this quotient, the exponential -2hn, which is not so important, and this quotient. So I'm just going to denote this quotient as exponential -l 1n-1, and this quotient as exponential -r n+1n with these notations. Why is it interesting to look at these quantities? In fact, we have already done so earlier on. We have with the random matrix products, we studied these coefficients, and in fact we considered the action of the matrix on the projective space. This means we studied how the matrix acts. In fact, we have established what is the recursion satisfied by L. In fact, by L n. Okay. Let me just rewrite the definition of this versus L. In fact, So the recursion satisfied by this process L in terms of the variable L is exactly what we have, what I mentioned earlier, which is this action. So it's B gamma of L and plus H. And plus so we already understand quite well these variables. So with this expression, the aim is to show that what's inside the parenthesis here is very large, either positive or negative. But if it's very large, it's the probability, the overall probability is going to be close to 0 or to 1. And you want to show that actually it's positive when sigma n, when you're in an ascending stretch, and negative when you're in a descending stretch. So let's first focus on the fact that this is large, so not close to 0, either positive or negative. As I said, you have this recursion. So as soon as n is not too close to the boundaries, so 1 and capital N, the variables which are involved here are going to be distributed close, well, not exactly, but approximately distributed like the invariant measure of this recursion, which I recall can be to first order, it's approximately like the uniform measure on minus gamma gamma. So it's of order gamma. Also, this process R, it satisfies also a recursion, but rather in the backward direction. So it's in terms of little n that you have this recursion. So with the indices in the backward direction, but also when you are far away from the boundary, this is going to be distributed essentially as mu gamma, which is close to the uniform measure on minus gamma gamma. So this is of order gamma. This is also of order gamma. This is of order 1, and also these three quantities are independent. So you can deduce that overall this is of order gamma. So it's typically large. It's going to be of order 1 only with probability 1 over gamma. This is what will eventually contribute to the discrepancy here, the 1 over gamma here. So okay, and the final step is to establish when it's positive, when it's negative. There you need some additional work, but maybe I can say a few words about that. It's okay. I'm already past time, so
Yeah, maybe 2 more minutes.
yeah. Okay, so I will just conclude. So we have given the confirmation that the Fisher configuration captures the trajectoral behavior of the random field Ising chain. In this case of the central field, we would like to get a sharper description and to explain what exactly contributes to the discrepancy. Maybe I'll say a few words about that. We have established. We have described the configuration with maximal energy. Now the question is, how can you deviate slightly from this maximal energy? There are different possibilities. The first is to have your wall fluctuate around the position of the minimum. So it's typically we will expect it to fluctuate like a random worker in a random environment. And we're fairly confident that this will be the case. But the problem is that these workers are not independent. So at some point they will meet, and in particular, if there are some stretches which have height just at least larger than gamma, it's typically just okay. So imagine this is just slightly larger than gamma, the height here. Then switching this spin domain, removing this spin domain will make you lose some energy, but not too much. So this might typically happen with positive probability. So this is also a behavior which contributes to the discrepancy that a full on a full gamma stretch, the spins may switch. Okay. And then there is also the case of the non-centered field, and there the claims made by Fisher are really not okay, because okay, some results are available for the free energy, and the description given by Fisher does not capture correctly the behavior of the free energy. It captures the right order, but it's not the right constant. And we believe we can. Well, I have a work in progress that needs to be written, but you need to refine a bit the description, and it's not this time you don't have one configuration, but you also have you have some additional randomness. So you have regions which are interesting to consider, where typically the configuration will want to put spin domains, but it's not as deterministic. You have to add some randomness. Okay, thank you.
So are there any questions or comments? This was an online, maybe you can raise your hand.
These products of random matrices, physicists also study them in the replicator. You can no, has it been done? You compare what kind of
So you said the replicator to study.
because we are doing essentially this some average on this age, the log function. So that is what we do with the trick that you do instead the average of the partition function to some power n.
Okay.
Take the limit of n to 0.
Yes. Well, here we haven't looked at it that way, so I wouldn't know. Okay.
Another question. Let's thank the speaker again. And we will resume in 10 minutes. So then stop.